Imagine for a second that you've been tasked with building a fully functioning software program.
Okay.
It has to read sensors, it has to perform logic, and, physically control hardware.
Right. Standard embedded stuff.
Exactly. But here is the catch.
Uh-huh.
You have a hard limit on your storage space. And I'm not talking about gigabytes.
Oh, I know where this is going.
Yeah, I'm not even talking about megabytes. You have exactly 2 kilobytes of storage to work with.
Wow, 2.
Just 2. I mean, to put that in perspective for you, a blank text document on your computer is probably larger than that.
Oh, easily.
A single emoji that you send in a group chat might actually carry more data overhead than that.
Yeah, it probably does.
But in this scenario, that microscopic 2 kilobytes, it has to hold your entire program, your logic, your instructions, literally everything.
It really forces a complete paradigm shift, doesn't it?
Oh, completely.
Because when you are operating with that kind of microscopic footprint, you start to realize how much of modern software relies on these invisible safety nets. You don't have an operating system managing memory for you. You can't just import some massive library of pre-written code just to, I don't know, blink a light.
Yeah, you can't just type import blink and be done with it.
Exactly.
Yeah.
Every single instruction you give the processor has this outsized cost. You are working directly with the bare metal of the machine.
Which is exactly what makes today's deep dive into the absolute bleeding edge of software minimalism so compelling.
It really is a fascinating topic.
So we are looking at an experimental programming project called Mecrisp-Across.
Right.
And this isn't from some massive tech conglomerate, right? It's a tool built over 7 years, from 2016 to 2023.
Yeah, by a single developer, Matthias Koch.
Just one guy.
Yeah.
And our mission today is to figure out how this tool manages to squeeze unprecedented performance out of hardware that honestly belongs in a digital museum.
It's true.
And what that extreme niche teaches us about the whole philosophy of how modern software architecture is actually built.
Well, it's a perfect case study in constraints. I mean, the hardware we're talking about here is the Texas Instruments MSP430 family of microcontrollers.
Right, the MSP430.
Yeah, specifically, the documentation focuses on chips like the MSP430F 2012.
Which is tiny.
It is. That chip has the 2 kilobytes of flash memory you mentioned, and an almost comically small 128 bytes of RAM.
Wait. 128 bytes, not kilobytes, bytes.
Bytes. Literally 128 individual bytes of working memory.
Okay, 128 bytes is, it's barely enough to remember a short grocery list.
Let alone run active computations, yeah.
And so if I'm a developer, how do I even begin to write code for a chip that small? Because usually the language itself takes up space, right?
Right, and that is the core problem here.
But you have to put the language on the chip.
Traditionally, yes. If you write code in a language like Forthword, which, by the way, is what Mecrisp-Across is based on,
Okay.
you usually have to put a kernel or an interpreter onto the target chip first.
Oh, so the chip has to be taught how to read the language before it can run the program.
Exactly. The chip needs to be taught how to read and execute the forth commands. It needs a dictionary of terms sitting on the chip.
Which takes up a ton of space.
Which takes up precious space.
Yeah.
But Koch designed Mecrisp-Across as what's called a zero-kernel cross-compiler.
Zero kernel. So it leaves nothing behind.
Absolutely nothing. It leaves zero trace of itself behind on the chip.
Meaning the target chip doesn't get the dictionary at all.
Nope. The microcontroller receives zero runtime overhead. There is no interpreter sitting there waiting for instructions.
Wow.
Every single byte of that 2 kilobyte flash memory is dedicated purely to the user code you wrote.
Okay, so the translation, like the heavy lifting of turning human-readable code into microscopic machine instructions, that's happening somewhere else entirely.
Yes. It happens on a separate host machine.
Got it.
The setup requires a much more powerful ARM-based system. So you might use a Linux machine running an emulator like QEMU,
Okay.
or maybe a development board like the Tiva TM4C1294, or an STM32F407.
So a beefy computer.
Exactly. That host runs a robust version of Forth, and it maintains a massive 64 kilobyte target dictionary in its own memory.
Oh, I see.
So it compiles the code there, completely separate from the tiny target chip.
I think I need an analogy here to ground this, because compiling for a system while actively avoiding putting the compiler on the system is a bit of a brain bender.
It is, yeah.
It feels like,
Okay.
Imagine an architect being hired to build an incredibly intricate house.
Sure.
But instead of the builder setting up scaffolding on the property and dragging in blueprints and, living on the site until the house is finished.
Right, which takes up space on the lot.
Exactly. Instead of doing that, they set up a massive command center miles away.
Ooh, I like this.
And they use remote-controlled robots to assemble the house perfectly.
Yeah.
And then when the final nail is driven, the robots just vanish.
Poof.
Yeah. If you walk through the finished house, there's absolutely no evidence of how it was built.
Yeah.
Just the final pristine structure.
That is a great way to put it. That captures the zero kernel aspect beautifully. The scaffolding and the blueprints stay at the command center. Only the final optimized house remains.
Right.
But we have to take that analogy a step further to really understand the truly unique part of Mecrisp-Across, which is the tethered aspect.
Good.
Yeah. How does the architect test the plumbing in that house while sitting in the command center miles away?
Right. Because if you write the code on a giant ARM machine, you might think it works perfectly, but you don't actually know until it's running on the tiny chip.
Exactly.
So how do you actually interact with it?
So Koch designed an emulated inner interpreter. When you are developing, you write your code in what's called target mode on the powerful host machine.
Okay.
And you interactively test the code right there, with the host basically pretending to be the tiny MSP430 chip.
But emulation is just a sandbox.
Right.
It isn't the real physical world.
True. And that is where the tethering mechanism is just brilliant.
How so?
When your emulated code reaches a point where it needs to interact with the physical world, let's say, it needs to read the voltage on a specific physical hardware pin.
Okay.
The host dynamically pauses the emulation. It reaches out over a physical connection, grabs the real data from the target chip, brings it back, and feeds it into the emulation.
Wait, really? It bridges the gap between the sandbox and the real hardware on the fly.
On the fly.
But how is it physically doing that without an interpreter on the target chip to receive the request? Like, how does the chip know what the host is asking?
It exploits a hardware debugging feature called JTAG.
Okay.
Specifically, a tiny two-wire version of it called the SPY-by-wire protocol.
Here's SPY-by-wire.
Kitschy! Very. So the powerful host machine essentially forces the target chip to comply by manually pulsing electricity down those two wires.
Whoa.
It's a technique developers call bit banging.
Bit banging.
Yeah. The host bit bangs the protocol, forces the chip to read its own physical voltage, pulls that reading back over the wires, and just hands it to your emulated code.
That is legitimately brilliant. You get the interactive testing experience of a massive computer, but with the real-world physical inputs of the tiny microcontroller.
Exactly.
It's basically using the diagnostic ports to puppet the chip.
That's a perfect description. Puppet the chip.
But if we, pull back from the technical wizardry of this for a second, what is the practical application?
Practical application.
Yeah, let's say I'm building a commercial product using these tiny microcontrollers. Why do I care so much about leaving zero trace of the compiler behind? Does it really matter?
Oh, it matters a lot. Because it fundamentally solves a massive legal headache. Licensing.
Licensing.
Yep.
Because if the robotic builders leave their tools in the house, you're bound by their tool rental agreements.
That is the reality of software development. The compiler itself is often licensed under really restrictive open source agreements, like the GPL v3.
Okay, right.
If you leave a fourth kernel on your chip, your user code has to constantly interact with that kernel to function.
And legally, those two pieces of software are now intertwined.
Exactly. Which can encumber your final product with the GPL v3 license requirements. You might actually be forced to open source your proprietary code just because you left the tools in the house.
Wow. But with Mecrisp-Across, since the compiler is entirely stripped away,
yes,
the resulting binary file is just pure, unadulterated machine code.
Completely unencumbered. The GPL v3 license applies to the host compiler, not the raw machine code it spits out.
So you own that final binary completely.
You own it 100%.
Okay, so the legal and architectural hurdles force us to leave nothing but pure code on the chip.
Right.
But we still have the physical hurdle. We still only have 2 kilobytes of flash memory and 128 bytes of RAM.
The physical constraints are severe.
How does the host actually complex fourth code down to that size?
Well, it requires a compilation pipeline that borders on obsessive.
Obsessive.
Truly. It isn't just about translating words to machine code. It's about fundamentally restructuring the logic itself. The first thing the compiler does is translate the human-readable code into an intermediate representation, or IR.
IR.
Yeah. It breaks everything down into foundational signals and tokens.
So it basically strips away all the human syntax and distills it into raw logical concepts.
Yes, because raw concepts are much easier for an algorithm to manipulate.
Make sense?
Once it has that IR, it performs usage tracking. It looks at the reset vector, which is basically the starting point of the program, and it maps out every possible path the code could ever take.
Every path.
Every single one. And if a piece of code is never physically reached by any path, it is ruthlessly deleted.
PID code elimination.
Exactly.
So if I write a whole complex function for reading a temperature sensor, but I forget to actually call that function in my main loop,
the compiler won't even send it to the chip.
not a single byte of it.
Not a single byte. And honestly, it gets more aggressive from there.
How much more aggressive can you get than ruthless deletion?
Well, it analyzes the code that is used, and it looks for functions that are only called exactly once.
Okay, and if it finds one?
It doesn't bother creating a standalone function. It just pastes that logic directly into the spot where it's needed. It's a process called automatic inlining.
Wait, let me think about that. Why is that better? Isn't the code the same size either way?
Well, the code logic is the same, but the architecture around it isn't.
Oh, I see.
When a processor jumps to a separate function, it has to save its current location, jump to the new code, execute it, and then figure out how to jump back.
Oh, right. And all of that jumping requires overhead instructions.
Exactly. Extra bytes. By pasting the code inline, you eliminate the jump entirely.
You're saving memory by taking away the processor's commute.
That's a great way to put it. No commute.
Amazing.
But the crown jewel of this optimization pipeline, without a doubt, is the register allocation.
Okay, talk to me about registers.
This is where we have to talk about how the chip actually stores data while it's thinking.
Right, because we only have 128 bytes of standard RAM.
And you want to avoid using that RAM as much as physically possible.
Because it's slow. Slow, and it takes extra instructions to access. Instead, the MSP430 processor has 10 available registers numbered R6 through R15.
Okay.
You can think of RAM as like a filing cabinet across the room,
Whoa, right.
whereas registers are the tiny workspace right on the CPU's desk. Accessing the filing cabinet takes time and overhead. Accessing the desk is instant.
So Mecrisp-Across tries to keep all the active data on the desk.
Exactly. It manages a deeply complex juggling act on the host machine to ensure the target uses those 10 registers perfectly.
Wow.
It can map up to 6 elements from the data stack and 4 from the return stack directly into those registers.
Sounds efficient.
It is, but the problem is code branches.
Right, like if statements.
Yeah. If you have an if-then statement, one branch might leave a piece of data in register 6, but the other branch might leave it in register 7.
Oh, man. And when the code merges back together, the processor would be completely confused about where its data is.
Exactly. And hand-coding that reconciliation in assembly language is incredibly tedious and error-prone.
I can imagine.
But the Mecrisp-Across compiler handles all of that multipass convergence on the host.
It figures it out automatically.
Yeah. It takes snapshots of the register states at every single merge point, and it inserts the exact microscopic instructions needed to ensure everything lines up perfectly.
So the target chip doesn't even have to think about memory management.
Not at all. It just executes perfectly choreographed steps.
That level of orchestration is just wild to me.
It really is.
But I want to talk about one specific trick that genuinely confused me when I was reading the documentation.
Which one?
The constant generator exploitation.
Oh, yes. The CG register.
Yeah. The notes mention that using common numbers costs 0 memory. And I'm just like, how is that possible? A number is data. Data requires storage.
It sounds totally impossible until you understand this quirky piece of the hardware. The MSP430 chip has a specific piece of hardware called the CG register, the constant generator. The engineers at Texas Instruments realized that certain numbers are used constantly in basic math and logic. 0, 1, 2, 4, 8, and -1.
Right, things you need for checking if a value is empty or like incrementing a counter by 1.
Exactly. So they hardwired a specific register to instantly provide those numbers.
Wait, hardwired?
Yeah. And Mecrisp-Across exploits this ruthlessly. If your code tells a variable to add 1 to itself, the compiler doesn't write the number 1 into your 2 kilobyte flash memory.
It doesn't.
Nope. It just points the instruction to the constant generator register.
Oh my God, it's using the physical architecture of the silicon to avoid storing software data.
That's exactly it. It is hardware-level constant folding.
That is wild.
And the compiler combines operations too. It uses what's called trampoline optimization.
Trampoline optimization.
Yeah. So if your code needs to make a decision, say, checking if a sensor value is greater than a threshold normally, that requires 2 instructions.
Okay.
First, perform the comparison. Second, branch the code based on the result.
Makes sense.
Mecrisp-Across fuses the comparison and the branch into a single, highly efficient jump instruction.
It really sounds like it's micromanaging every single clock cycle.
It absolutely is.
Even with unexpected events, right?
Yeah.
Because the documentation mentions interrupt-aware framing.
Yes.
And from what I understand, when a processor gets an interrupt like a sensor, suddenly demanding attention, it usually panics.
Basically.
It dumps all the data from its desk into the filing cabinet, handles the emergency, and then pulls everything back out.
That is the standard, safe way to handle an interrupt. You save all the registers just in case.
Right.
But Mecrisp-Across doesn't do safe and bloated. It does bespoke tailoring.
Naturally.
It analyzes the specific interrupt service routine, the tiny piece of code meant to handle that emergency, and determines exactly which registers it will touch.
Oh, wow.
And it only saves and restores those specific registers.
So if the emergency only requires 2 items on the desk, it doesn't sweep the whole desk into a box. It just moves those 2 items.
Exactly, which saves precious clock cycles and precious bytes of RAM. It treats every single interrupt as a unique optimization problem.
Okay, let's look at the actual concrete results of all this micromanagement, because the numbers in the source material are honestly staggering.
They are.
They built a Blinky program, right?
Yeah.
Which is basically the hardware equivalent of printing Hello World on a screen.
Right, it just toggles an LED on and off.
Yeah. But this version uses an 8 megahertz oscillator and requires a highly precise millisecond delay function.
Not trivial.
Exactly. And Mecrisp-Across compiled that entire precise program down to exactly 70 bytes of flash memory.
70 bytes.
70 bytes.
And by the way, it uses 0 bytes of user RAM.
None of the 128 bytes.
0.
And if you rewrite it to be an IRQ, Blinky, meaning the LED toggling is driven by hardware interrupts from the watchdog timer, it's even smaller.
Yeah.
46 bytes of flash.
It's incredible.
The entire interrupt service routine that handles the timer takes up exactly 6 bytes.
It really is a masterclass in extreme code density.
Okay, I hear that, and I respect the technical achievement. I really do. But I have to push back here.
Go for it.
In 2026, the laptop sitting in front of me has 16 gigabytes of RAM. Storage is practically free. A 70-byte program is a neat parlor trick, sure. But why wouldn't a developer just write the code in standard C using a standard compiler?
Well,
Or, if they really truly needed it to be 70 bytes, why not just write it directly in raw assembly language? Why build an incredibly complex tethered forth cross-compiler for this?
that is the fundamental question of utility. And the answer is that Mecrisp-Across occupies a very specific, very punishing middle ground.
Yeah.
Because if you write in standard embedded C, the language inherently carries boilerplate overhead.
C brings its own baggage.
Exactly. Trying to coerce a standard C compiler into producing a 70-byte Blinky while keeping your original source code readable and maintainable, it's incredibly difficult. C just wants to bring its own scaffolding.
Okay, so C is out if you're fighting for individual bytes. What about writing the raw assembly language yourself?
Well, you can absolutely achieve a 70-byte program in hand-tuned assembly.
Right.
But writing complex logic, especially math routines, interactive hardware testing, and dynamic memory management in pure assembly is absolute misery.
Misery.
Total misery. You, the human, have to manually track every single register state across every single branch of your code.
Oh, right. Because there's no compiler to do the multipass convergence for you.
Exactly. It is slow, tedious, and highly prone to catastrophic human error.
So Mecrisp-Across gives you the high-level interactive logic of Forth,
Yes.
but outputting the hyper-optimized machine code of an assembly master.
That's exactly it. It's for that specific scenario where you absolutely must utilize every single byte of a 2-kilobyte chip, but you still want the ability to actually test and interact with your code during development without losing your mind.
Okay, that actually makes perfect sense.
Yeah.
But that brings us to the inevitable reality check, doesn't it?
Yes, it does.
If this tool creates such miraculous, unencumbered, tiny binaries, why isn't it the industry standard? There are massive trade-offs required to achieve this level of minimalism, aren't there?
Absolutely massive. The source notes make no secret of the disadvantages.
Let's hear them.
First off, the documentation explicitly labels the project as experimental in all capital letters.
All caps experimental. That usually translates to use at your own risk.
Basically, this is not a consumer-ready plug-and-play framework.
Right.
And the structural limits are severe. For example, the compiler fundamentally does not support recursion.
Wait, what? A function cannot call itself.
Nope.
But That's a pretty standard programming technique. Why can't it do that?
Remember that multi-pass register allocation we discussed earlier?
Oh, yeah, where it maps out the flow of data through the registers.
Exactly. The compiler needs to perfectly map out that flow. If a function can call itself infinitely, the compiler can no longer predict the memory footprint or the register state.
It basically creates a math problem the compiler can't solve.
Right, so recursion is entirely off the table.
Wow. Okay, what else?
Well, you also have to deal with the learning curve. The documentation notes that the source code comments are entirely in German.
Oh, boy.
Yeah, plus you are locked into a hard-coded memory map for a single microcontroller family.
So if your supply chain changes and you have to switch from the MSP430 to an ARM chip,
You can't just flip a toggle in a menu. You would have to completely rebuild the cross-compiler from the ground up for the new architecture.
that's brutal.
And furthermore, you are writing in a non-standard forth syntax.
Non-standard.
Yeah. For instance, traditional forth allows certain flexibility with commands like create. But Mecrisp-Across strictly demands an end-create pairing. You are essentially learning a unique dialect just for this tool.
But the biggest trade-off, the thing that really underlines the experimental label, is the fragility of the cross-compile cycle itself, right?
Oh, definitely.
Because the notes highlight that the connection between the host and the target is notoriously unstable.
It is the Achilles heel of the entire system. It relies on an incredibly complex dictionary save and restore mechanism.
And earlier you mentioned the host is managing a massive 64 kilobyte target dictionary.
Exactly.
Yeah.
To interactively test and reflash the chip, the host tries to take a snapshot of that massive dynamic dictionary state using a specific forth command structure called builds does.
Builds does.
Yeah. Forth is unique because it allows you to build custom compilers inside the compiler while it runs.
That sounds like Inception.
It is.
Yeah.
Attempting to freeze that highly dynamic meta-compilation state, wipe the tiny target chip, and then flawlessly resync the entire system without corruption is incredibly difficult.
It honestly sounds like trying to write a complex novel.
Hmm.
But every time you want to add a new chapter, you have to perfectly recreate the entire world building and character history from a memory snapshot.
Yeah.
And if you get one detail wrong, the whole book burns.
That is a very accurate way to visualize it. If you flash the target chip, test an input, change one line of code, and try to reflash, the state often corrupts.
So what do users do?
They practically have to restart the entire host environment for every new compilation just to guarantee it works.
Wow. Which explains the reality of the user base.
It does.
The documentation notes stats from 2019. The community consisted of exactly one author, Matthias Koch, one financial donor, and exactly one active tester.
It is the ultimate solo passion project. It exists because someone wanted to solve a hyper-specific, incredibly difficult puzzle.
Not because they were trying to capture a massive market share.
Exactly.
So let's pull all of this together. Most people listening to this are never going to write code for a 2 kilobyte microcontroller.
Probably not, no.
They will never worry about JTAG, bit banging, or the constant generator register. So why does Mecrisp-Across matter?
Because it is a mirror held up to the bloat of modern software.
Bloat.
Yeah. When you open a web browser today, millions of lines of code are acting as invisible scaffolding. Massive frameworks are managing memory, allocating registers, and handling errors.
And we just accept that immense overhead because we have the gigabytes of RAM to absorb it.
Exactly, but Mecrisp-Across proves that absolute crystalline efficiency is still possible.
It shows us what happens when you refuse to leave the scaffolding inside the final structure.
Right.
The disappearing compiler uses immense complexity on the development side to ensure absolute simplicity on the execution side. It perfectly shapes its creation and then vanishes entirely, leaving behind only what is absolutely necessary to function.
Beautifully said.
Which leaves us with a final thought to ponder as we wrap up. If we look beyond the realm of microchips and code, what other complex systems in our modern world would function better if their compilers worked this way?
That's interesting.
Think about the middlemen, the administrative frameworks, the massive bureaucracies we navigate daily just to get things done. What if those systems were designed to completely disappear the moment the actual work was finished, leaving behind no overhead, no maintenance, and no trace?
A lot less bloat, that's for sure.
Exactly. Something to think about.
Yep.
Thanks for joining us on this deep dive. We'll catch you next time.